All right, welcome to the exciting conclusion of our rabbits versus sheep adventure. Because so far, we studied the population of rabbits and sheep who compete for the same resources, such as hay. And we let x of t to be the population of rabbits at time t, and similar for y of t to be the population of sheep at time t. And we found the following model, which relates sort of the interaction between the bunnies and the sheep, which was simply x prime equals 3x minus 2x squared minus xy. So xy is the interaction between the two, and y prime is 2y minus y squared minus xy. And the question we were trying to answer is, what happens in the long run? In the long run, will one of the populations die out? Will they coexist? Watch this video to find out. And then furthermore, we did find the equilibrium points. So equilibria. So we found that there are 4 of them. So 0, 0, which again means no rabbit, no sheep. They both die out. That's unstable. We have 0, 2. So no rabbits, but maximum number of sheep, which is a saddle. All that was done in the previous video. And then there is maximum number of rabbits. So 3.5 and 0 and no sheep, which is also saddle. And finally, 1, 1, half rabbits, half sheep, which is stable. And so in other words, we got the following picture so far. Kind of like this. Again, 0, 0, which was unstable. 0, 2, and 3.5, 0, which was saddle. And by the way, the orientation here will be confirmed soon. And 1, 1. Okay. And now the question is, how do we complete the picture? And in this case, what we want to do, we want to study the behavior of rabbits and sheep on several different axes. So we really want to consider the following rectangle. So one axis will be y equals 0. So no sheep. One will be x equals 0. Hopefully I can draw that. Like this, x equals 0, meaning no rabbits. X equals 3/2. So rabbits are at maximum capacity, and y equals 2. So sheep are at their maximum capacity. And now we will see what is going on each of those axes. And that will help us figure out what's going on. Okay, so let's first of all do x equals 0. X equals 0, meaning there are no rabbits. And see what happens to our population model. So I like to remind you, our differential equation was x prime equals 3x minus 2x squared minus xy. Y prime is 2y minus y squared minus xy. Now, if x is 0, again, that's just a specific point, so we can still calculate x prime. In this case, it would be 3 times 0 minus 2 times 0 squared minus 0y, and y prime, that is 2y minus y squared minus 0y. And what this gives you is x prime is 0, and y prime, you can factor this out, it's just y times 2 minus y. However, in our region, so in the box above, we can actually, so this axis here, we can actually figure out the sign of y prime because, well, y is positive and also less than 2. So in fact, if y is positive and less than 2, this means y prime is greater than equal to 0. So since 0, y, since y is between 0 and 2. Meaning that if there are no rabbits, then y will increase. So y prime is 0, so y increasing until we reach our max population. Until y equals 2, in which case the sheep die out. Or like actually stay there. Max population. And you can see this in the picture above. So again, if there are no rabbits, then the sheep population will increase until we reach the population of 2. So already by studying this axis, we can figure it out. And similarly, I will not do this. If there are no sheep, then we expect the rabbits to increase until it reaches 3/2. So case 2. Y equals 0, no sheep. And then this means x increases until we get x equals 3/2, which is again the max population. And makes sense. If there's no sheep, the rabbits evolve independently, so they will eat up all the hay until they reach the limiting population of 3/2. So there's those two axes, and then the last ones we want to talk about are y equals 2 and x equals 3/2. So here, x equals 3/2. So what happens if the rabbits are at the max population, and what happens when the sheep are at the max population? So case 2. Case 3 in this case. So let's assume that, let's see, y equals 2. So max sheep, or in other words, sheep reach the carrying capacity. Then our differential equation in this case becomes x prime equals 3x minus 2x squared minus x times 2. Again, minus xy, and then y prime is 2y, so 2 times 2, minus y squared, so minus 2 squared, minus x times 2. In which case we get x prime equals x minus 2x squared, and y prime, in this case, it's minus 2x. So in other words, x prime is x times 1 minus 2x, and then y prime is minus 2x. Now, x prime is a little bit harder to study, but what's much easier to study is this y prime, because in this case, y prime is negative, and so once again, in this case, y prime is negative, which really means here that y decreases. And in fact, we can put this on the picture above by just saying that the arrows point down. So let's go back to this axis. And we don't really know how they point, like southeast or southwest, but in this case, all we can tell so far is that they point down, maybe like this. Which again here means that if the sheep are the carrying capacity at the max population, they will eventually decrease. And that's because of competition with rabbits. So let me write that down and then we'll continue. Okay. So if sheep are at max capacity, they will decrease due to competition. With rabbits. Because they already have all that hay, but then rabbits also want hay. So naturally, the sheep population will decrease. And last but not least, same thing if the rabbits are at the max capacity. And then we also see that X will go down as well due to competition. And you can write this on the picture above as follows. So X decreasing, X is like left or right. So everything will point to the left in this case. So maybe like that. And that already completes our picture. And the cool thing is, now if we look at this carefully, it seems that all the arrows are pointing to 1, 1. And in fact, this is what's going on. If you're actually in this box, it seems that everything will converge to this stable equilibrium point. In fact, let me show you a couple of nicer pictures. Whoa, I know, magic, isn't it? So here on the left, once again, you can see the picture with the axes, with the arrows pointing in several different directions. And now we see that we can complete the picture. So the cool thing is we're actually able to answer a question. So epic conclusion. So turns out the two species will actually not go extinct. These two species won't go extinct. They will actually happily coexist. They will coexist and eventually reach the equilibrium 1, 1. So eventually the rabbit population will be 1 and the sheep population will be 1 as well. 2, 1, 1. Except, dramatic music. What if they actually cycle back and forth? What if there's a periodic orbit like that? But if you're interested, you can check out the notes and you can see that this won't happen. And essentially, in case you're curious, suppose it goes counterclockwise like that, then what you can do, you can study the population on those two axes, and you will see that it will not really match with the arrows. Because for instance, I think you can show the arrows like go this way, and which won't match with it going up like that. And similarly, if you do it in the clockwise direction. All right, I hope you really enjoyed this population adventure. I think that was a really cool application of nonlinear ODEs and of the tricks that we learned.